Hello again, guys. I'm back, as I promised you, with an example of a body that is going through combination of translation and rotation. And in this case, we have a disc or a wheel that is rotating clockwise with an omega and actually accelerating in the same direction with the radius of the wheel being to 10 inch. All right, and given at this instant, the instant shown, omega of the body is 4 radians per second, so this is 4, and alpha of the body is 6 radians per second, as shown here. And we want to find acceleration of A, we want to find acceleration of B, acceleration of C, and acceleration of D. So again, B is right on the rim on top of A, C is the contact point, and D is right on the rim on exactly this horizontal line. All right. So I want to start with the acceleration of it. You guys remember in the previous video, in the sequence that I put probably in the email, or I'm going to put it in the email soon for your class, for rolling motion and no sliding, remember. You saw at the end of that video that acceleration of the center, and this is only for the center of the wheel. It is going to become R alpha, which is 10 times 6 equal to 60 inches per second in the horizontal and in the direction of alpha. Since alpha is rolling or actually accelerating, the wheel physically is rolling clockwise, but it's also accelerating. So that's acceleration of A, which is 90 degrees to this radius. Okay, remember again, I keep emphasizing that this is only for the center of the wheel, guys. No other point. So you can't say, oh, acceleration of B is going to be this new R. That's not going to work. Okay, you'll see in a minute. All right, now how do we go about finding acceleration of B, acceleration of C, and acceleration of D? Very easily. Just like the video you have seen in the past for velocity analysis. You want to find the acceleration of B, no problem. Use A as your reference for the translation part of the motion. So this is translation with respect to A. And this is the rotation with respect to A. Okay? So remember, what does this second part of this equation mean? What does this mean? It means find acceleration of B as if A is fixed. So if I make A fixed here, right, make it the pivot point, and I want to find acceleration of B, remember, there are two components, and that's what makes velocity analysis different than acceleration. For velocity, we just had R omega. But now we have the normal acceleration, R omega squared, which points toward the center of rotation, right? That's your AN, and A sub t, which follows alpha. And they're equal to R omega squared and R alpha. So I calculated them here for you. R is 10, omega is 4, so we get 160 here. And R alpha becomes 60. And look at the direction. So I came down here and I said, okay, look, acceleration of B is acceleration of A. 60 is acceleration of A, which we got here. Plus, what is acceleration of B relative to A? There is a tangential component, 60, and there is a normal component, which is this guy, 160. Remember, don't go and try to find the resultant of these two. Not a good idea, because you have to have them broken into horizontal and vertical components anyway. All right, so what I did, I said 60 plus 60 is 120, and then 160 here, so a component, 120 horizontal and 160 vertically down. When you add those two, vectorially of course, like this, 120 and 160, you get 200. So let's go back, say acceleration of B actually is 200, like this. It was what? 120 and 160. Okay, so this is acceleration of B equal to 200 inches per second squared. All right, back here. Now, what do we do for acceleration of C? Exactly the same thing. Use the same equation, this time translate with A and rotate about A. So this is acceleration of C as if A is fixed. Let's go back. Acceleration of C as if A is fixed. So what's going to be that? This is point C. Two components, a normal component and a tangential component. See, normal points toward the center, tangential follows what? Alpha. We already have them here. Is this exactly the same thing? R omega squared and R alpha. So that's not going to change. going to get 160 and 60, right? R is 10, omega is 4. R times alpha, R is 10, alpha is 6. Okay? So what I did, I said, okay, acceleration of A again is 60. Acceleration of C relative to A, two components, this guy and the normal component, I put them here. 60 and 60 cancel one another. So acceleration of C only becomes that component 160 pointing up. So here we go. Acceleration of C is going to be like that at this instant, equal to 160 inches per second squared. So now that leaves us with acceleration of point D. So nothing different, just use the same equation, translate with A and rotate about A. Let's go back. This acceleration of D relative to A means what? Find acceleration of D as if A is fixed. We have the picture already here. If A is fixed again, A is fixed. What is acceleration of this point? Again, two components. A normal component toward the center and a tangential component pointing down in the direction of alpha, right? And again, they are exactly the same. It's just that the components, they have different direction. The AN is 160, the AT is 60. So come over here, acceleration of A is 60. Acceleration of D relative to A is a 160 to the left and a 60 down. 60 to the right, 160 to the left becomes 100, the difference, right? 100 to the left plus 60 down. So a 100 to the left and a 60 down will give you acceleration of D. And go ahead and find the square root of 100 squared plus 60 squared, and you get 116.62. So that was the last point we wanted to find the acceleration. So that comes out to be, I just lost it here, something like this. So that's acceleration of D. All right, I hope this has made sense to you, and this should wrap up all the videos for this week, and then we have one last week, the week of, I believe, April 6th, if I'm not wrong. I gotta take a look at my calendar here. And yeah, it does look like the week of April 6th. We'll talk about our last chapter, which is chapter 17, and that's the rigid body problems, kinetics of rigid bodies using modified second law. As always, thanks for watching and listening.